Thank you very much for coming to my talk. I'll be talking about a strange phenomenon that we see in systems like Lenia, and this one in particular is in a variant called asymptotic Lenia. Okay, so just first to introduce the concept of continuous cellular automata. Just to start with the charismatic part, the creatures that you find inside these rules. So unlike the legacy of discrete cellular automata like Conway's Game of Life and the cellular automata in that family, the continuous CA are defined with variously defined with continuous values, space and time. And many of you know about Lenia already, but I'll just briefly introduce how it works. You have some sense of, is this better? Okay, you have some sense of locality, and you get that from convolution with a neighborhood kernel. It's like a continuous version of the Moore neighborhood or von Neumann neighborhoods you might have in the earlier CAs that were discrete. And then you have some dynamics. In this case, it's a growth function, and these are often defined as a Gaussian. So that's a bell-shaped function you see on the right. Now, if you want to see that written out as an equation, it's the state plus an update. And then the important part for today is that the next states of the grid will be constrained by this by these pink parts here. This is a clipping function to truncate the values of the next grid state between 0 and 1. So other than that, it looks a lot like, it looks exactly like the Euler method, where you have the current state of the system plus the change in the system. That's the growth function here. And that's proportional to some step size, and that's delta t, the step size in time. There's pseudocode there which writes out the same thing if you prefer to see it written out as code. Now, visually, that will look something like this, where you first calculate the neighborhoods by convolution with the neighborhood kernel. It's convolution of the original cell states of the grid. And then that fuzzy looking image on the left will be the results. That's the neighborhoods. And those neighborhoods are fed to the growth function we looked at earlier. And that gives you the update. And we add that to the pre-existing cell states to get the cell states at the next point in time. Okay, so here's an example of one of the most charismatic and most archetypical gliders in Lenia. This is in the Orbium family. And you'll probably notice immediately that you can see all the little pixels. It's quite grainy and coarse. And of course, this was simulated on a computer. And Rudy Rocker described discretization as the necessary evil that you incur when you're simulating continuous cellular automata with computers. But computers are very fast. So if we want to be more fine with our simulation, we can just make those simulation parameters more fine. So in this case, I'm decreasing the step size dt and also the spatial resolution, which you do by increasing the radius of the kernel. So the spatial resolution is 1 over the kernel radius here. So that's why it looks like we're zooming in, because the concept of space is changing, the smallest element of space. And it's also a little bit slower because the step size, the frame rate is the same, but the slice of time for each update is smaller. So we can have finer simulations at the cost of more computation. And really, this is just limited by how fine you want to be. Of course, nothing terrible could possibly happen if you make the simulation more accurate. That would only happen if you made the simulation too coarse. Oh, well, I suppose that sometimes because things are a bit unexpected. It turns out that in this particular set of simulation parameters for this particular point in rule space, the glider is only stable at a certain coarseness of simulation. And I'm just going to take a little aside to introduce asymptotic Lenia, and the reason for that will become clear on the next slide. It's a very similar formulation to the original Lenia, but instead of a growth function, you have a target function. And so this is actually backwards. So the target function is subtracted from the pre-existing grid state. So this should actually be over here. So it should be A x and t naught. So it should have the target function, that's the purple one, t, subtracted from that. I think that this was reverted somehow. But anyway, you'll notice, aside from that mistake in how this is presented, you'll notice that there's no truncation function for asymptotic Lenia. So unlike the original Lenia, which we saw earlier, you don't have to restrict the values between 0 and 1 because that comes for free. So here in the pseudocode, you can see the correct ordering. So A minus the target function. Okay, and so here's why we're interested in looking at asymptotic Lenia today. So in previous work by, I think this was at last year's A-Life by Kojima and Ikigami, they found, so this was an incidental result for something else that they were doing. They found a particular orbium that was unstable with too small of a step size, but they found that when they removed the clipping function at that small step size, it was now stable. There was the trade-off where at the larger step size, the original step size was now unstable. But they then started to think that maybe the clipping function has something to do with the instability that you get at small step sizes for some patterns. And asymptotic Lenia doesn't have that. And indeed, they didn't find any gliders in asymptotic Lenia that had the same sort of instability due to small step sizes. So in general, I call this instability when the simulation is more fine, non-platonic. And so this would be with respect to any of the simulation parameters. So we're concentrating on step size here, the temporal resolution, but you could also find non-platonism in spatial resolution or numerical precision are other places where I've seen it. Okay, so in order to see if I could find an example of a glider in asymptotic Lenia that would be non-platonic, I first had to find a new point in rule space that has interesting dynamics. And this will be a little bit simplified. I'm only going through the width of the growth or the target function, the sigma here. And in this first case, when it's too large, growth occurs too readily, and we have a space filling rule. So I've started with a bunch of different patches. They're all randomly initialized, but the same according to the same. In each example, I'll show the patches are different, but between the different settings, they're the same. On the other hand, if you make this particular parameter too small, then you don't have any growth and everything disappears. So this particular search space was easy enough and tractable enough to follow the gradient manually. And we're getting a little bit closer. And finally, we see some of the patches disappear, some of the patches grow, and you can probably tell where I'm going to pick the gliders out of. Okay, so there are these moving tips of the growth in the grid, and I'll just crop those out from the background. The green space here are the parts that I set to 0. And then if we just run the simulation for a while, then the glider does the rest of it. It pulls itself together with the sharp edges that have been cropped out. And also have some nice glider collisions in this one. All right, so now the moment of truth. You can now find out if the title of this talk was a joke or if I'll actually show a result with where asymptotic Lenia can be non-platonic. And I'll mention that the other thing that I did when I was searching for an interesting rule space is that I was searching with the step size already a bit large, so 0.25, whereas many of the most interesting gliders in Lenia are found with a step size of 0.1. Okay, so as you saw, the glider eventually loses its ability to cohere to itself. It loses its self-organization capabilities. And as a summary of this fairly simple result, here are a few example trajectories where we have a step size of 0.2 of the glider leading to persistence. This glider will continue for as long as I'm willing to run it. And but at a step size that's too small, 0.17, it disappears, and it also disappears following the intuition you'd expect in general from simulating physics with computers, where if you are too coarse, there will be some sort of catastrophe and non-realistic simulation. So, and then on the right-hand side here, we have a map of a large parameter sweep. So the green darker area is the areas that were stable for the duration that I was running it. And then blue indicates unstable by way of vanishing. And if you have particularly good eyes, you may see that there's about 1 pixel's worth at the end of this arrow. And this inset is that 1 pixel's worth. So that's about, it's about 1,000 times zoom. And there's still some fine structure in there. And so this result of a non-platonic glider in asymptotic Lenia was actually kind of incidental to another project, or other side of this project, which was just examining the retention of fine detail at various scales. And indeed, these boundaries between stability and instability for these types of CA tend to be somewhat fractal. And here the zoom will be a little bit more than 4 orders of magnitude from the original overview. And so there's some fine detail all the way down to the point where the computer can no longer represent fine detail when we run into floating point error. Okay, so that's all I have. That's the result. I've seen this non-platonic behavior in a lot of different systems that follow this state plus update rule, but I sometimes forget about the truncation that's apparent in Lenia, and I sometimes even write it down without it. So when I read this result from last year in the absence of non-platonic behavior in asymptotic Lenia, I thought it was worth investigating. It's not something that I normally considered. So at this point, I'll take any questions you might have.